time for us to do some practice involving parameterized curves, which means tracing where a particle moves through space, where there's this extra parameter. As always, it's important to do practice so we get used to doing things, especially when we have a new idea. So if you're following along, consider making use of the pause button. So you can say, hey, I wonder how this one goes. Pause it, try it out, see how you do. If you ever need any help, just unpause me and I'll come along and give you a hand. Well, let's begin. So our very first problem, it's actually pretty straightforward. It's a matching problem. I don't know if we've done one of these. For each of the following parameterized curves, select the corresponding plot from the ones given below and put your answer by writing the label of the plot in the box. So when we talk about a plot of a parameterized curve, what we're really talking about is just imagine that you mark every single point. So you have t varying from some range. You go through for each value t, there's like a dot, 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 dot. And if you mark them all, what do you see? What's the picture that emerges? So oftentimes the question is, do we care about the parameterization or do we care about the curve? And it depends on context. There are some cases where we say, well, we don't care about how it's parameterized. We just care what the curve is, in which case we pick a good parameterization. There are cases where we say, we care about how things are moving along the curve, and in that case we pay attention. Generally speaking, we're going to be more on the, we don't really care how we travel along the curve. We just want to figure it out. So let's think about what we can do here. Let's start with the first one. That seems like pretty straightforward. Whenever you see a t comma something, that's, we can think of this like what we thought of before. Maybe we can think of this first coordinate is x and the second coordinate is y. Now that's always true, but notice how you have x equals t and y is t squared. Well, that says y is x squared. So in other words, whatever your x value is, y is x squared. So we say, aha, this would correspond to y equals x squared. Now, you'll notice that there's a lot of curves that look like parts of x squared. Well, not this one. All right. But what else do we see? Well, it says we're going from -1 to 1. So that's where x goes from. So we say, okay, so x goes from -1 to 1. Well, which one does that? And the picture here, we see the picture, there's only one of them that goes from -1 to 1. You see, this one goes from 0 up to something. This goes from 0 up to something. This one looks like it goes from -1 to 1, but it's not a x squared, because it's upside down. The other thing is, notice the circles here. An open circle means that we don't include that point, whereas a closed circle says we do include the point. Notice that we are including our endpoints. So that says, hey, we would include our endpoints here. And so that says, good, that's E. So we're going to mark this one as E. Now, let's do our next one. So 2 over pi arctangent of t and 4 over pi squared arctangent of t squared. You say, what? That looks crazy. But if we have the same philosophy, we say, well, look, if we think of this as x and we think of this as y, we say, well, really, if you square the x, see, 2 over pi squared would be 4 over pi squared. Square arctangent, you get arctangent squared. So we say, aha, this is still along y equals x squared. They might say, well, wait, hold on. But these don't go off towards infinity. Well, we're not saying it goes to infinity. Be careful. We're saying that the time goes off to infinity, but that doesn't mean the curve has to. Curve might not go towards infinity. It depends on how it's been parameterized. So we got to think about arctangent. Well, we know arctangent, I hope. And what happens? Well, arctangent does the following. It approaches this asymptote of pi over 2 as you head off towards infinity. So at 0, we're at 0. And then as you head towards infinity, you get closer and closer to pi over 2. So in particular, if we just think about what's happening to x, we see that the arctangent of t times 2 over pi, well, let's just do arctangent of t. Arctangent goes from 0 up to pi over 2. I'm marking the range for arctangent from 0 to infinity. Now you scale by 2 over pi, that says, hey, lo and behold, we can now say that our x value is going to start at 0, and it's going to get close to 1 but never quite reach 1. So we're looking for part of x squared where we definitely start at 0 and include it, and we look like we're getting close to 1, but we don't include 1. So that would be this one. C, right? Start at 0. As we move along, we get close to something but never quite reach it. So, C. Good. Progress. 2 down, 3 to go. Well, you probably can see how this game is being played. Now, this one. Sine of pi t, 1 minus cosine squared of pi t. And we're going from -1 to 1. Now, of course, if we weren't paying attention, we would say, oh, I see like a 1 minus something squared. That looks like d. And we would say, oh, -1 to 1, and we don't include the endpoints, perfect. And then we write down d. But we are going to pay attention. We're going to pay so much attention that even if that's the right answer, we're not just going to rush into it. We don't want to commit too early. We're a little bit hesitant to say, look, I'm not willing to commit to anything long term until I'm more certain about what's going on. So let's think about what's going on. Is there a nice relationship between the x and the y? So 1 minus cosine squared, is there another way to write that? Well, there is, because we know our trig identities. So what happens is we could say this is really like sine of pi t, and 1 minus cosine squared is like sine squared. And now we say, so this is not an upside down parabola, it's just a normal parabola. Okay, so that tells us, hey, again, we have something like y equals x squared. So it's part of our parabola. So it's actually not d. They were trying to mislead us, but we saw through their charade. So what is it? Which one is it? Well, now let's think about what's happening here. We're told time goes from -1 to 1. Let's focus on what happens with our input, if we think of that as our x value. So sine of pi t from -1 to 1 does what? Well, it does the following. We actually get a full, -1 to +1. See, normally sine starts at -pi into pi, but because we have that factor of pi on the inside, we need to go from -1 to 1. Now, where does x go? Well, here's the thing. Where does it start? It starts at 0, right? But we don't include it because we're not including -1. And then as we move down, we see, okay, the x value goes down, and it goes down to -1. Then the x value moves up, and keeps moving up to +1, and then it keeps going down again until it goes back to 0, but doesn't quite reach it. So, what can we say about the range of the x values? We can say that our x values are going to go from -1 to +1, and we will include the x values. Now, it doesn't seem like we should, so you have to remember that there's this subtle distinction going on here. That whatever the t is does not force whatever the output is. And you might say, well, wait, the endpoints for t are included. And we say, that's perfectly fine. What's going to happen here is the following. It says, you don't quite start at 0, but you come out away from 0. You go up, and then you turn back around, cross through, go up, turn back around, then head back in. So what we can't see in this parameterization is the fact that we actually cross through things twice. So the curve doesn't indicate that. Well, that's one of the dangers. If we just see the plot, we don't necessarily see the behavior of how many times we traverse the curve. But in terms of like what is the output like, what's the correct plot, the answer is it's going to be E again. Now you might see this and you might say, whoa, wait a second, that's a repeat. We never said that we couldn't repeat. Be careful. See, sometimes a lot of people are like, aha, if I see a matching problem, I just start matching things up and I throw out, if I match things up with E before, I'll never see E again. Throw it out and done with it. But sometimes you might be in the case where it says, oh, actually, I can represent the same figure in multiple ways. And so you have to be open to the possibility that there might be more than one way to represent the situation. This is probably the most interesting one. And I suspect D was a red herring because that 1 minus cosine squared, that's making us think like 1 minus x squared. Yeah, I think D, it was a temptation for us to put D there. Thank goodness we didn't yield to that temptation right away. Okay, well, rounding the corner, what do we see? Well, 1 minus t cubed, and there's t to the 6th minus 2t cubed plus 1. Well, if you recognize that, you can say, hey, that's really 1 minus t cubed for the x coordinate. Whoops, that's a comma. That's a huge comma. And t to the 6th minus 2t cubed plus 1, that looks scary because it's a 6th-degree polynomial. It's the same as 1 minus t cubed squared. So we're back to, again, y equals x squared. But now we have to think, okay, what's happening for our x coordinate? So we can figure out which part it is, because there's 4 candidates that involve y equals x squared. Notice we start at time 0. Well, at time 0 we included, and that would be at 1. So I want to include 1. So that rules out C. We've already ruled out D. So we're down to 2 possibilities. As time goes to 1, 1 minus t cubed goes to 0. But we don't reach it. See, I'd reach it if I had t equals 1, but I don't. So I want to go towards 0 but not reach it. And that means we'd want B. So that's the answer. Okay. Well, the last one. 1/2 times t plus 1. And then there's 1/4 t plus 1 squared. Well, we can see that is going to be, again, it's an x squared. Okay, so y equals x squared. Let's think about what's happening for our values. Now, it looks like -1 to 1. So again, we might say, oh, maybe it's E again. But we've learned our lesson. It's not that t indicates what happens with x. T indicates what happens with our parameter. We have to translate that into x. So let's think about what's happening with x. Where do we start? Plug it in. 1/2 times -1 plus 1 is 0. So we're going to start at 0. Where are we going to end? 1/2 times 1 plus 1 is 1. So we're going to start at 0, including 0. We're going to end at 1, including 1. And then it goes right in between. There's no like shooting out. So we go from 0 to 1. So this translates y equals x squared for 0 less than or equal to x less than or equal to 1. And that's the right picture. You see, it can't be B or C because they're missing some ends. It can't be E because we don't go negative. So it's A. And there we go. Ah, what a fun problem. What a fun, this one, the middle one. This is unexpected, I think. Well, it's unexpected if you're not paying attention. But we're going to pay attention, and so it shouldn't surprise us. Okay, let's do another one. Determine all t when the parameterized curve 2t minus sine squared t, t squared plus 2 cosine squared t plus 1 intersects the line y equals 2x. Well, what's our picture here? We have our space. So here's our space. And we have this line, y equals 2x. Well, that's easy to see. Here's y equals 2x. And then we have this curve that does something. It's not clear what it does. It looks like it'd be wiggly given that there's sines and cosines. Who knows? It's doing something. So the question becomes, well, so for what values of t do we intersect? In other words, do we have anything that does that, where that curve, as I move around through space, hits the line? Well, at first glance, it might seem, how could we solve this? But then we start thinking about it and say, wait a second, this is not so bad. Because if we think about what's going on, what we really have is that our x is 2t minus sine squared of t. And our y is t squared plus 2 cosine squared t plus 1. I mean, that's our parameterization. X equals something, y equals something. So if I want to ask, where does it hit the curve y equals 2x? We say to ourselves, well, what we'll do is we'll take this expression for x and we'll substitute in for x. And we'll take this expression for y and we'll substitute in for y. And now we say we'll get down to an equation only involving t. In particular, what will we get? Well, we'll intersect the curve y equals 2x only when t squared plus 2 cosine squared t plus 1 will be equal to 2 times 2t minus sine squared t. Now at this point, we might be getting a little nervous, because what do we see? Well, we see polynomial and trigonometry. Ooh, that's a dangerous combination when we're trying to solve. But maybe it'll work out. So we forge ahead. So okay, let's expand out. So in other words, multiply through by the 2. And this is a case where, again, we use one of our most powerful tools, something that helps save so many points. It's called parenthesis. You see, when you use parentheses, you're more likely to remember, oh yeah, I need to make sure I distribute to everything. It's not just that the 2, it goes and multiplies by the 2t, it also goes through and catches on to the sine squared t. So it goes through to both terms, the first and the second. Okay, so this would be 4t minus 2 sine squared t. So we'll move everything to one side. It's a pretty good standard rule because we like setting things equal to 0. 0 is just such a wonderful friend for us, a great ally. So we'll have t squared, I'll say subtract 4t, then we have the 2 cosine squared t, the 2 sine squared t, because it'll come over as a plus, and plus 1 equals 0. But now, we're saying, oh, 2 cosine squared, 2 sine squared. That was chosen very carefully so that it looks terrible, but actually it's not so bad because it becomes 2. Cosine squared plus sine squared equals 1. Then there's a factor of 2. So we say, okay, we really need the following. T squared minus 4t, 2 and 1 makes 3 equals 0. Well, that looks like it'll factor. And if it does, only one way it could do it, because 3 only breaks up as one way, namely 3 and 1. We see minus, so it would have to be t minus 3 and t minus 1 if it did factor. And you can check it. It works, right? T squared minus t minus 3t, that's minus 4t, and plus 3. So that leads us to the conclusion that t equals 1 and 3. So that's the times when we intersect. Now we have to make sure that's what we're looking for. And in this case it is. It says determine all the t. So these are all the t. If the problem had said find all the points where it intersects, we need to do one more step. If we were looking for all the points, we'd say, well, look, we can't stop at the times. We need the points. But that's not so bad. You take the times, plug it back into the parameterization, and that would produce the points. But for us, we're happy to stop here because that's our answer. So, woohoo! Good. Ah, that was a nice problem. We should get more problems like that, right? Of course, of course. All problems should be nice problems. All right. Well, find an equation for the tangent line to the parametric curve secant t tangent t at t equals pi fourths. Okay, well, let's think about it. What do we need? Well, if we need to find a tangent line, we need to find a line. Now, every line always has two pieces of information. We need to get a point, and we need to get a slope. So, how do we get these things? Well, the point, you plug in the parameter. See, we're at time pi over 4, plug it in. So our point would be secant of pi over 4, tangent of pi over 4. All right. We can even clean that up. We know what these are. Secant of pi over 4, it's a little bit less common, but it's not so bad. Think about cosine of pi over 4. Cosine of pi over 4 is 1 over root 2. So for secant, you flip it over, and secant of pi over 4 is root 2. Tangent of pi over 4, oh, that's one we should know by heart. We use it a lot. It's 1, tangent of a 45-degree angle. Okay, now we get to our slope. For our slope, we're about the derivative. So we should start by talking about our derivative. So we look at y prime over x prime. We start there. So we come to our y. So our y is tangent and our x is secant. So y prime, derivative of tangent, is secant squared. X prime, derivative of secant, is secant tangent. Now you can clean this up, and you can see, hey, we can cancel off a single secant. So we get this is secant of t over tangent of t. Now that's at any particular choice for t. So secant of t divided by tangent of t. Now, we're not quite done. What do we need to do? Well, we need to have a number. A slope is a number. It's not a function. So we have to evaluate. So at pi fourths, we get secant of pi over 4 over tangent of pi over 4, which we've already found out what these numbers are. Root 2 over 1 is root 2. So there we go. So there's our slope. Our slope is root 2. Now we have our point, and we have our slope, so we can make our line. So what does it turn out to be? Well, it turns out to be, we take y minus our y-coordinate, 1, is equal to our slope, root 2, x minus our x-coordinate, root 2. Or you could say y is equal to root 2 times x, and then you have root 2 times root 2, which would make that a minus 2, but you add 1 to that, so minus 1. And there you go. There you go. Now on a side note, the problem doesn't ask us to do this. We're actually done. But we can push just a little bit further if we're looking for saying, do we understand what's going on? So secant and tangent aren't just random. They often go together. And the reason they often go together is there's a beautiful trig identity that connects them. Namely, the trig identity, the following one that says tangent squared plus 1 is equal to secant squared. Well, if we think of x and y as being secant and tangent respectively, this says, oh, this is like y squared plus 1 is equal to x squared, or if you like, x squared minus y squared equals 1. So what happens is that if you let secant and tangent range over all possibilities, you get the following picture. Namely, you get what's called the hyperbola. And you can show asymptotically it approaches this line y equals x. Now, where are we at time pi over 4? Well, the answer is that we're somewhere over here. So this is our point, and we're asked to find the tangent line to that point. So we're after that point there, and that's has a negative intercept. Okay, that good. It all agrees. So essentially, that's the line we're looking for. So this is not such a crazy curve where we have our parameterization as secant and tangent. It's not so far off from the circle where the parameterization is sine and cosine. So, okay, anyways, a little side note, just for fun and education. That's what we're here for after all, right? For fun. In the meantime, if we learn something, that's a bonus. So let's move to our next problem. Find the tangent lines at all points where the parametric curve x of t equals t cubed minus t plus 1 and y of t equals 3t cubed plus t squared plus 6 intersects the line y equals 3x plus 1. So here we have a couple of steps. We know what we're looking for. Our final answer should be some tangent lines. But in the meantime, we have to say where. Well, we were told, look for where we intersect 3x plus 1. So we're going to sort of break it down into a couple steps. The first step, step 1, where do we intersect 3x plus 1? So that's important for us to know, because we can't start finding a tangent line until we know at what parameter value for t we should take our tangent line at. So where do we intersect y equals 3x plus 1? Okay, so for that, well, we say, look, we have y, we have x, so we plug in the y value for y, the x for x. When I said the y value, I really should say the expression for y. We plug that in, expression for x, we plug that in, and we'll get down to a single expression involving t, which lets us solve for t. And, ooh, cubic, woohoo! Try to flex our cubic muscles today. Well, we should try. Let's see. All right, so we get 3t cubed plus t squared plus 6. So that's our y value equals 3 t cubed minus t plus 1 and then plus 1. So again, in case we're trying to figure out where did everything come from, we have this as y equals 3x plus 1. And we're being very generous here with our parentheses. When in doubt, err on the side of too many parentheses instead of too few. So what do we do? Well, let's simplify. So we have 3t cubed plus t squared plus 6 equals 3t cubed minus 3t plus 3 and 1 more. So plus 4. And now, the 3t cubes, they're going to cancel. It's not a cubic. What a shame. Well, there's still hope. Someday, perhaps, we'll get to do one where it doesn't cancel. So the cubic parts cancel. We're left with t squared. And then here we'll move the 3t across, so plus 3t. Move the 4 across, plus 2 equals 0. Okay, well, that looks like only one way to factor. That would be as t minus 1 and t minus 2, because, t plus 1, t plus 2. See the plus because it's plus in the middle. We have to get 2. There's only one way to break 2 apart. 1 times 2. Check, of course, right? T squared plus 2t plus 2t. Yeah, that's t, 3t, and plus 2. Good. Good. It works. Well, so now we say, aha, that tells us our times. -1 and -2, which means we're going to have 2 answers. Okay. Well, that's okay. It's all right to have more than one answer. Sometimes things can happen in multiple different ways. Now, let's move towards the second part. The second part is now we know our parameter values where we're looking for tangent lines, -1 and -2. The next thing is find the lines. So, step 2, find our tangent lines. And to do this, it will probably be helpful to write down our slopes. So, recall that's y prime over x prime. So, y prime, come here, that would be 9t squared plus 2t. So taking the derivative of the y term, x prime would be 3t squared minus 1. All right. So let's do our lines. And here we go. At t equals -1. Well, what's our point? We carefully work through and plug in -1. -1 cubed would be -1, minus -1, plus 1, and plus 1. So -1 plus 1 plus 1. Y would be -3 plus 1 plus 6. Right? Because minus -1 cubed is -1. So, okay. So that gets us here. We get the x coordinate is 1, and the y coordinate is 7 minus 3 is 4. Okay, our slope. All right. So we'll have 9 minus 2 over 3 minus 1. 9 minus 2, 3 minus 1, which is 7/2. Now we have a point, we have a slope, so we can say, aha, that leads us to y minus 4 is equal to 7/2 x minus 1. Okay, and that's that one. And that's perfectly fine. That is a line, and we're just asked to find lines. And of course, if we wanted to, we could expand, rearrange. But if we're asked to find lines and not told any more specific instructions, that's good enough. Okay, how about at -2? Well, at -2, what happens? Well, what's our point? What do we have? So, -2 cubed is -8. Minus -2 plus 2. And then plus 1 more, comma. 3 times -2 cubed. Ooh, that's a big one. -2 cubed is -8. Times that by 3 is -24. -2 squared is 4, so we're going to add 4 and add 6 more. So -8 plus 2 plus 1 would get us up to -5. -24 plus 4 plus 6 would be -14. Okay, so, all right, a little bit bigger, but that's okay. No problem. How about our slope? Well, -2 squared, 4 times 9 is 36. 2 times -2, -4. Downstairs, 3 times -2 squared is 12, and -1. So that gets us up to 32 over 11. Okay, well that's going to be an interesting line. So y subtract -14 makes y plus 14 equals 32 elevenths, which is our slope, x subtract -5, which is x plus 5. And there we go. That's our other line. And now we found both lines. And so we're done. Those are our 2 lines. Good. All right. Woo, fun. So it's not so bad. It's got to think about what do you need to do first. You know, what's the right first step? Oftentimes in solving problems, that's the hardest part. Where do we begin? And how do you figure that out? Well, you do it through lots of practice, and you start thinking about pattern recognition. We've seen a problem like this before. What did we do in that case? And once we have that done, we start thinking, oh, we have this big backlog of problems that we can tap into. And that's why we do so many problems, so that we can develop that pattern matching ability. And so that's good. We should keep at it. we should keep doing more problems, because the more we do, the better we're going to get. So, our next problem. Find the derivative dy dx at time t equals 1 for this curve. This looks easy. We don't even have to find a line. We just have to find the derivative. Piece of cake. Piece of cake, right? Well, let's see what happens. So when we're looking for dy dx, we oftentimes write it as y prime of t over x prime of t. Now I'm going to tell you right now, one of the biggest mistakes I personally make when it comes to parameterized curve is when I'm not paying attention, I say, oh, I want y prime over x prime, and I think, okay, I'll just do the first one and the second one. But you got to remember which one is the y and which one is the x, because you don't want to confuse them. So when we're looking for y prime, even though it's the first thing that we're going to do, it's the second term here. So this is our y, and here this is our x. So be careful. I have made that mistake so many times, and so I'm going to be cautious so I don't make that mistake right now. But I will tell you, that's a common mistake. So here we go. 6t squared, okay, plus 6t, and minus 12. That's easy. And downstairs, derivative of x, 3t squared minus 3. Okay, great, perfect. And we're almost done. So at t equals 1, we plug it in. We get 6 plus 6 minus 12 over 3 minus 3, which is 0 over 0. Aha! And that means more work. More work. Because 0 over 0 doesn't mean it's 1. It doesn't mean it's 0. It means it's indeterminate. That's what 0 over 0 means. So this is more work. Okay. So the question becomes, well, what's going on? Now, oftentimes, when you do see 0 over 0, what's something you can do? Well, you say, well, take a limit as t goes to 1. What should it be, in other words? So that's sort of the right philosophy. What should it be? What should it be? So we're going to take a look at the limit as t goes to 1 of this expression and see if we can get a handle on it. Now, really, it doesn't really need to do limits here because we can actually see what's going on. It's polynomial over polynomial. The fact that we're getting zeros means we're getting things which factor. So if we dig into this polynomial expression, well, let's just skip this polynomial expression for a second here. Come back up here. See, that I can plot a 6. That's t squared plus t minus 2. And here I can plot a 3, t squared minus 1. Because when I plug in 1, I get 0 for both upstairs and downstairs, means, by the way, just do that really quickly, means that when it comes to factoring, one of my factors has to be a t minus 1, both in the upstairs and downstairs. It's not so hard to figure out what the other factor has to be. T squared minus 1 is easy to factor because it's a square minus a square. Whenever we see square minus square, it's a squared minus b squared is a minus b, a plus b. The upstairs is actually not so hard to factor either. It's t minus 1, and I say, look, it has to be t and something. Well, minus 1 times whatever I put here has to end up giving negative 2, so it'd be plus 2. So, boom, boom. So, what we really have is, other than at time t equals 1, what we can say is our expression is 2 times t plus 2 divided by t plus 1. Okay, so that's how our derivative behaves everywhere other than time t equals 1. Well, so we plug t equals 1 into this, and that should be how it behaves at time t equals 1 as well. So this goes to 2 times 1 plus 2 over 1 plus 1, which is 3. And that's what we'll do to think of the derivative. Now, before we walk away from this one, I will say, you might say, okay, so does that mean that our tangent line has slope 3? And yes, that's a good way to think about it. But oftentimes when you have this 0 over 0, there is something a little bit interesting going on in the following sense. Now, I don't know exactly where we're at time t equals 1, but we know we have a slope of 3 here. So what tends to go on when we have this type of behavior here is that it locally won't actually look like a line. It's going to look a little bit different. And that it's not going to come along this line and then come off, but it tends to be more of a cusp. So oftentimes if you do get a 0 over 0, not all the time, but what you will have is more of a cusp-like possibility. If you were to go out and plot this, and there's lots of things that plot parametric curves, you would see probably it looks something like this, or it might be going in the other direction. I'm not sure without doing more work. And I want to be careful. I'll let the computer. Computers love to plot, because how does a computer plot? It does lots of little computations, and they love doing lots of little computations. So we will sometimes cheat a little bit and say, oh, it's the tangent line. It is true that in terms of a linear function, it is behaving most like this line. Although the function itself is sort of only like a half line, whatever that means. If this is confusing you, don't worry about it. Just let it go. But if it's like, oh, interesting, okay, good. Well, it's nice to think about things that are a little bit different. Okay, one last problem. For now, right? More problems later, but one problem to finish up for now. Find an equation for the tangent line to the parametric curve given by x of t equals t cubed minus 4t plus 5 and y of t equals t to the fourth plus 3t squared minus 7t at time t equals 1. And then also determine if the curve is concave up or concave down at that time. Okay, well, the first part shouldn't be so bad. It's about finding a tangent line. So let's get into it. So how do we begin? Well, we think about what's going on. So for the tangent line, we say if we need a line, we need two pieces of information, a point and a slope. And that's because if we're looking for a line, we always need two pieces of information, a point and a slope. Tangent line is no different. So for the point, we plug in 1. So for our x value, we're going to get 1 minus 4 plus 5. For our y value, we'll get 1 plus 3 minus 7. This is why we like working with 1. It's so easy to plug in. So here, 6 minus 4 will give an x value of 2. 4 minus 7 will give a y value of negative 3. Okay, so that wasn't so bad. How about for our slope? So for our slope is y prime of t over x prime of t. So what does that become? Well, that's going to become y prime. There's y prime. Got to be careful. You know, I often confuse. You know, which one is y and which one is x. That's y. So 4t cubed plus 6t minus 7. And divide that by 3t squared minus 4. And that's it, right? Yes, good. So 4t cubed plus 6t minus 7, the derivative of y, 3t squared minus 4, derivative of x. And now we're like, okay, great. At x equals, t equals 1, t, what do we have? Well, we get 4 plus 6 minus 7 upstairs and 3 minus 4 downstairs. So that's 10 minus 7 is 3 over negative 1 or negative 3. So there's our slope, negative 3. All right, well, that's good. Now we have our slope. Well, what's next? Well, the next thing for us to do is put it together, and we'll have our answer to the first part. So we say, given our point and our slope, we can say our line is that y minus our y value, so minus minus makes a plus 3, is equal to our slope, negative 3, x minus 2, which we can clean up. That's y equals minus 3x, because we distribute that through, and then it'll be a plus 6, minus 3 times minus 2 is plus 6, and then if we subtract 3, it'll become plus 3. So y equals minus 3x plus 3. Yes? Okay, good. All right, there we go. Now, that is our tangent line. But there's an also question. What's the also question? Is the curve concave up or concave down? Well, that deals with concavity. So how do we get a handle on that? Well, for that, we need to go into our second derivative. So let's start digging into it. Now, how do we do our second derivative? Well, we can think of it, if we remember how our second derivative works, our second derivative is oftentimes the derivative of the derivative. So we can think of our second derivative, d squared y dx squared, says you're taking the derivative with respect to x of dy dx. Now, here's where you got to be careful when you're working with parametric curves. It doesn't just mean, oh, take two derivatives of y or two derivatives of x. Well, the way we should really think about it is we should say, well, we're going to take the derivative of the expression for the slope, which is dy dx, over the derivative of x, because we're saying, how does our slope change as our x changes? So that says we're going to take the derivative of this expression, 4t cubed plus 6t minus 7 over 3t squared minus 4 over the derivative of our expression for x, the t cubed minus 4t plus 5. Okay, now we get into it. By the way, if you just remember the formula and you're like, oh, can I just use the formula? Yes, you can. Absolutely. If you remember the formula, do it. And life is good. But if you don't remember the formula, just think about, okay, I'm taking the derivative of the slope over the derivative of x, and that's good enough. Okay, so, and the top, well, quotient rule. So, take the bottom times the derivative of the top, 12t squared plus 6, minus the top, 4t cubed plus 6t minus 7 times the derivative of the bottom, 6t, all over the bottom, the bottom term squared. And then if you look at this term, it's again the derivative of t cubed minus 4t plus 5 is another 3t squared minus 4. So actually, if you just go, doop, so turn that square to a cube, and there you go. So that's how you compute the second derivative at a given time per t. Well, now we just plug in our time per t, and we'll see what we get. So at t equals 1, because we're at time t equals 1, and we'll just go through and plug in 1. 1's a great number to work with. 3 minus 4. So that's minus 1, 12 plus 6, 18. Minus 4 plus 6 is 10. Subtract 7 is 3. So 3, 6. Divide by 3 minus 4 is minus 1 cubed. Okay, so I just want to double check. 3 minus 4, yep, negative 1, 12 plus 6, 18, yep. Here, 10 minus 7, 3, good. 6, yep, that's all good. Don't forget the minus. So we have minus 18 minus another 18. That looks very negative, but we're also dividing by a negative because negative 1 cubed is negative 1. So if we put all the signs together, what happens? We end up with a positive 36. Now, in terms of concavity, concavity is worrying about the sign. So, are we concave up or are we concave down? The answer is we're concave up. Wherever the second derivative is positive, we're concave up. Okay, so that answers the second part. Now, why would we want to ask this question? In some sense, what we're doing is we're trying to say, maybe we have a parametric curve and we're trying to get a sense of the behavior of what's happening at a particular point. Now, when I look at the tangent line gives me sort of a nice local behavior. And so we now can say, just off of our tangent line, that we have the following information. We know we go through the point 2, -3. So let's say this is our point 2, -3. And our tangent line looks something like this. So locally it looks like that. But now we can ask the question, well, how does the curve fit into this picture? In other words, is it on that side or is it on this side? And how can you figure that out? That's where the second derivative comes into play. The second derivative tells you how the curve sort of comes off the tangent line. The way to remember it is when the second derivative is positive, that says you're coming off the positive side of the tangent line. When your second derivative is negative, that means you come off the negative side. And in some sense, the magnitude just tells you how quickly you come off. A larger number tends to come off much faster than a smaller number would. So this is telling us that locally we're coming off in that way. So if you were to go out and to plot this parametric curve and you were to look at the point 2, -3, it would nearby look something vaguely like that. So that's why we might be interested in looking at the concavity, the second derivative. And okay, well that's that problem, and we're done. Good. Well, lots of good practice. Of course, we should always do more, but we'll save that for another session, right? All right. Take care.